Welcome to this video. Video number 11 in my series of videos on Georg Cantor's 1895 and 1897 articles on the theory of aggregates and transfinite numbers. Section 11 is titled The Ordinal Type Theta of the Linear Continuum X. At the start of this section, Cantor doesn't elaborate on what is meant by real number here. It would seem that Cantor quite expectedly takes a fairly usual view of what is meant by a real number, and what is meant by the linear continuum, which is the aggregate of all real numbers x, with x greater than or equal to 0, and x less than or equal to 1 in their natural order of precedence. So in this particular case, the symbol used to indicate a simple ordering is effectively synonymous with the less than relation between elements of x. That is, x is of lower rank than x primed in x, if and only if x is less than x primed. The linear continuum is briefly shown to be a perfect aggregate, using the terms introduced in section 10. Anyone with some familiarity with the basic results of classical real analysis won't be surprised at all by this result. The theorem on page 134 is a theorem which characterizes the ordinal type of the linear continuum. Compare this with the result from section 9 which characterizes the ordinal type eta. The aim of the theorem is to show that the aggregate M of the theorem has ordinal type theta. That is, the ordinal type of the linear continuum. However, M itself is not to be understood as being an aggregate of real numbers. The proof of this theorem is not difficult in principle. The most difficult thing for me personally is just to keep track of the different fundamental series involved. Other than that, there isn't anything major that I need to elaborate on. The assumption that S, that is the aggregate with cardinal number Lf0, which is contained in the aggregate M of the theorem, has no highest element and no lowest element, ensures that S has the ordinal type eta. If S has a highest and or a lowest element, then the ordinal type will be slightly different to eta, such as 1 plus eta plus 1 or eta plus 1, and so on. But nevertheless, assuming that S has the ordinal type eta retains the full generality of the proof. Note that part B of the theorem assumes that between any two elements M0 and M1 of M, elements of S lie. But towards the end of the page we're told that since S is a part of M, between any two elements S0 and S1 of S, other elements of S must, by B, lie. The reasoning behind this may go as follows. Suppose S0 and S1 are elements of S. Then they are also elements of M, since S is a partial aggregate of M. And so by B, there must be an element S2 of S between S0 and S1. Therefore, between any 2 points of M, there are elements of S. That S and R are similar aggregates implies, by definition, that there is an imaging of R on S. The assertion is that from the imaging of R on S, we are able to extend this imaging in a suitable way to give an imaging of X on M. That X0 can be regarded as a limiting element of the fundamental series X nu contained in X is due to the fact that X is a perfect aggregate, and thus every element of X is a principal element, that is, a limiting element of some fundamental series in X. Since it is also known that to each real number x in X, there is a sequence of rational numbers which converges to X, then the assertion that we can replace the fundamental series X nu with a coherent fundamental series R kappa nu in R is justified, since R is contained in X, and thus elements of R can be considered as elements of X. Moreover, since X nu has limiting element X0, and R kappa nu also has limiting element X0, then by theorem D, these series must be coherent. Theorem E from section 10 justifies the following claim that R kappa nu in R corresponds to a series S lambda nu in S. Recall that we have assumed a definite imaging of R on S, and that this series in S must have a limit in M. The latter claim is also because the series in S can be considered as a series in M, and since M is perfect by A of the theorem, then the series in S must have a limiting element M0 in M. Moreover, since X0 does not belong to R, then M0 cannot belong to S by theorem F of section 10. That is, if M0 were in S, then X0 would have to be an element of R and vice versa. The one-to-one correspondence between X and M is formed which shows that X and M are equivalent, but we've yet to show similarity. That is, we still have to show that the correspondence preserves the order relations of the elements of X and M. Since the correspondence between the elements of R and the elements of S was assumed to be an imaging, then the order relation of the elements of R and S respectively is preserved. We still have to check the rest of the elements of X and M respectively. The argument showing that the correspondence between X and M is an imaging of the whole of X on M is fairly straightforward and relies on the definitions of limiting elements of fundamental series. A few cases are considered. The first is, if two elements of X are chosen, one of which is an element of R and the other not, and with R less than X naught, then it's shown that the corresponding elements of M, that is, S and M naught, are also such that S precedes M naught in M. Note that the general symbol to represent an order relation has to be used for M, since the relation less than is not defined on M. The second case is similar to the first, but with R greater than X naught, and then finally, the case where both elements of X chosen are not elements of R. The details are fairly self-explanatory and don't really require any further explanation. Thank you for watching. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on various topics on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.